Okay, so we're going to talk about adding a hydroxide to an alkene. And so we've got these four here, and we're actually not going to talk about this bottom one, the halohydrin formation, mostly in this video, mostly because it's a little bit more closely related to adding an adding a halogen to an alkene. So the mechanism for that, even though it's adding an OH and a halogen, it's more closely related to the halogen, so we'll save that for another time. But we'll talk about these three right here. So we have the acid-catalyzed hydration, hydroboration-oxidation, and oxymercuration-demercuration. So we have those three. What we do want to think about for any of these reactions is we have two main issues when we're adding something. We have regioselectivity to worry about, and that's like where on the molecule is it adding? Is it adding on the more substituted Markovnikov or the less substituted, which is the anti-Markovnikov? We also have stereoselectivity to think about. So stereoselectivity, what that means is syn means it's adding to the same side of the alkene. Anti means it's adding to opposite sides of the alkene. Racemic means it's adding any which direction. So hydroboration-oxidation is the only one that's anti-Markovnikov, and it also adds syn in stereoselectivity. These two, acid-catalyzed hydration and oxymercuration-demercuration, those are going to be added racemic, but they're also going to be both Markovnikov. And so the interesting thing about these two is that they're in the same box. So you think like maybe they're going to end up being the same thing in terms of like predict the products. But these are actually really tricky, and so we want to look at the mechanisms to see the difference between these two. Even though they're both in the same box, both adding Markovnikov and racemic, we have a little bit of something else to worry about, specifically with acid-catalyzed hydration, that we don't have with oxymercuration-demercuration. So let's look at those and the mechanisms for them. So for acid-catalyzed hydration, we've seen this before. We're just adding water with catalytic amounts of H2SO4. So I'm not going to go through this mechanism in the video. What I want you guys to do is I want you to pause it, try to figure out what that would be. Go ahead and do that mechanism for yourself. And try to figure out what this final product would be. I'm going to show you what it looks like. Pause it, double check your work, and then we'll move forward. So go ahead and pause it now. Here's what the mechanism looks like. So go ahead and pause it and take a look at it, and then here's our final product. Just double check yourself, check your work, and make sure that you did this okay. Okay, so the final product ends up looking something like this. I have my phenyl and my OH added here. So notice that that's not even where the alkene was. That's because we had a carbocation rearrangement in our mechanism. So acid-catalyzed hydration, we got to worry about carbocation rearrangement. Over here in oxymercuration-demercuration, we don't have to worry about carbocation rearrangement, because it doesn't go through a carbocation intermediate. So this is racemic. This is also racemic. We could have R or S for either of those. Now technically the hydrogen that was added is could be one way or the other way. Now it's also technically not racemic because it's not a stereocenter. But you could think about it as having added racemic, although it's just not going to matter because it's not a stereocenter. Okay, so there's the product for acid-catalyzed hydration. Now what about oxymercuration-demercuration? So this one, in this reaction, what we do, first off, we add Hg, and we have this parentheses, OAC, parentheses, 2. Now I'll show you what that looks like when we do the mechanism. And we also add it with water. One cool thing about this reaction is it doesn't necessarily have to be water. You could add an alcohol instead of water, and that would give you an OR group coming off of instead of an OH. But if you add water, it's H2O, adds the OH. So that's cool. The second step of that is the demercuration part. So for that one, we add sodium borohydride, sodium hydroxide, and water. So that's our last step. So let's look at the mechanism. We'll come back and write our final product. So let's look at that mechanism. First of all, what does HGOAC2 even look like? Interesting. So it looks like this. We have mercury here. And connected to mercury, I have two acetate groups. O and then the acetate groups. So interestingly enough, the first thing that happens is I actually just lose one of those acetate groups. He just leaves. And I end up making this. Because that was a really good leaving group. So now I've made this. Now this is an excellent electrophile. This is an excellent electrophile. And remember last time we talked about how double bonds, pi bonds, can be nucleophiles or bases. So that is going to act as a nucleophile and attack my electrophile. So this guy is going to come over here. Really long arrow. He's going to attack the mercury, and it's going to kind of do this like weird thing where the mercury is going to clap back and attack there. It's a strange thing. So we're going to end up with this weird intermediate that looks akin to an epoxide, although it's clearly not an epoxide. So my phenyl is still wedged. Now this guy is going to add one way or the other because it's going to be an epoxide type thing. So either I'm going to add on that wedge there, now my mercury is plus charged again. I started off net positive charge, I end up with a net positive charge. That's really good to keep in mind. Then I have that, or actually not or, and we're gonna have both. We'll have both of those. Now this is where water comes in. So remember we talked about this, how this one is going to be Markovnikov addition. I'm just going to show one of them as my representative. So Markovnikov addition means that it's adding to the more substituted side. That makes sense because this looks like an epoxide that's been protonated. And we know that if I'm adding to a protonated epoxide, I'll add to the more substituted side because it goes through a carbocation-like intermediate. So I'm going to add to the more substituted side when I have something that looks like a protonated epoxide because it goes through a carbocation-like intermediate. So this guy's going to come over here and he's going to move that mercury off in a way. So my attachment to the phenyl, that has not changed its stereochemistry. When we had the carbocation rearrangement, it ended up losing stereochemistry, but that guy has not been touched this whole time, and he'll stay that way. So now my methyl group is wedged, my O is dashed, and my mercury is wedged and neutral. I'm going to neutralize this guy by reacting it with water. So that's what my molecule looks like at the end of the first step. So all of this, all the way through here, is just step one. And so I got to get all the way to the end of step one before I can begin step two. Now, it's important that we remember that this is not our only product. I also have what would have been this guy. So that's the end of step one. Now, step two, I don't think you need to know the mechanism for it, really. It's interesting because in a lot of ways, they're not really going to show it to you in much detail. It is kind of not as clear-cut as maybe the book makes it out to be. It's kind of like maybe a radical elimination, which kind of ends up destroying the stereochemistry of where the mercury is, which is confusing. It's fine. Everything's fine. It's weird, but we don't really have to worry about that too much. You can think about it as like an SN2-like thing, but know that it's a little bit less clear than that. So step two, sodium borohydride comes in, gets rid of that mercury. That's the demercuration part. This is the oxymercuration. Step two is the demercuration. So what we end up with is a product where the phenyl has stayed intact. That's still a wedge up to that phenyl. And then that spot right there is racemic. So we'll fill that in. So this has been a Markovnikov addition, but the stereochemistry on that site is racemic. Now the last one is hydroboration-oxidation. So hydroboration-oxidation is quite interesting, and it's a little bit weird. So the first step of hydroboration-oxidation, we're going to have BH3 with tetrahydrofuran, THF. And then step two, that's the hydroboration part. The oxidation is when we kind of get rid of it. And so we have H2O2, sodium hydroxide, and water. So we'll come back and fill this part in, and we'll assess what happens after we do that mechanism. So the first part, BH3 with THF. So what we need to know this is just like what we talked about in recitation, how so alkenes are planar. They can approach something from one face or the other face. I can't simultaneously hit something with an alkene on maybe my palm and this part of my hand, like the fingernails or something like that. Like it's either got to hit this way or this way. There's no bending and rotating of alkenes. They're planar. They're going to hit this way or this way. So that's why this BH3 mechanism is going to be syn addition. The stereoselectivity is going to be syn addition because the BH3 is going to approach the alkene either this way or this way. So let's look at what that looks like. So my BH3, here he is. So he's going to approach So he comes and approaches this alkene. And so the interesting thing about this is this ends up making a 4-membered ring transition state. So this ends up making this weird transition state that I'll try to show for you. It's not a perfect transition state by any means, but it'll do. That's a dash. My bad. Okay. So this pi bond is breaking at the same time that this sigma bond is forming, and this sigma bond is forming, and then this sigma bond is breaking. So these bonds are breaking, the ones that I just highlighted there. These bonds are forming. And the reason that it's going to end up adding anti-Markovnikov, it's not that it just suddenly became acceptable to have a less substituted like carbocation-like intermediate, but it is the case that maybe this bond forms last in the whole process of the transition state. So this is the more substituted carbocation for the longest amount of time. So this bond between this carbon and that hydrogen kind of forms last. Now you don't really need to know how to show that and all that, so it's not, you know, super pertinent. But this is the kind of the intermediate, like the transition state that we're going to go through. And so what ends up happening I've added my hydrogen on there. That's going to be a racemic addition, technically. But let's just say, okay, this is dashed, this part, and this is wedged. Our boron ends up adding whatever direction the hydrogen ends up adding, because remember, it's approaching from this side or this side. So I have this product and this product. So this is not the end of the first step. This is just the first part of the first step. So I'm going to call this R. This whole group here, that's R. This process happens twice more because look, we have 2 more hydrogens to go. So this is part of step 1, this is part of step 1, and this is part of step 1. Happens twice more. I end up making this, where I have 3 of these R groups on my boron. That is the end of the first step. I've finished the first step. Now I have 3 carbon groups on the boron. Then we can begin the second step. So we can start off the second step by this. I have this, because what happens when we react this H2O2, it's going to react with sodium hydroxide and make this product where I have a negatively charged oxygen right there, and that is going to act as a nucleophile and attack this electrophile. Lewis base is going to attack the Lewis acid. And so I'm going to end up making something that's very interesting. I'm going to end up making this. And so what happens in this reaction is I do this weird push-pull mechanism. So I take this bond right here and I move it over, I attack that oxygen. That's the push part. Then I pull and I break this OO bond. That's a really weak bond. I just break that off. And so what ends up happening after that step is I end up with something that looks like this. So I'm not quite done. This needs to happen twice more because I have 2 more of these R groups on my boron that need to become OR groups. Remember, I need to try to get an oxygen onto my alkene. And so step 2 happens twice more. This step and then this step happens twice more for each of these 2 R's. So I will end up with this. Then we can do more nucleophilic and electrophilic additions with the OHs. We'll end up finishing out this mechanism by ending up with 3 alcohols and 1 borate salt. So our final product over here is going to be anti-Markovnikov and syn addition. So it's important that I show both of them. So I'm going to show maybe the wedged methyl, the dashed hydrogen, and the dash OH, syn addition, plus, now I can't just say plus an enantiomer because I have a whole nother stereocenter here that does not change. Oh, no, I ran out of space. I'll draw them down here. Sorry, that's a little tough to see. I'll redraw it over here. Anyway, this is the mechanism for that hydroboration-oxidation. I end up with 2 separate molecules with important stereochemistry that I need to show. Great. So this is the 3 main ways that we can add an OH onto an alkene. I hope that this has been helpful in clarifying some of that. I know it's kind of long and drawn out, but if you guys have any questions, feel free to comment about it, and then we can also talk about it in our Zoom recitations. Thanks.